Modern gold recovery operations require immense physical footprints. These terraced mounds are the result of constant stacking and containment across hundreds of acres. Conveyor systems run around the clock to stockpile crushed ore, layering reddish-brown rock into mountain-sized heaps. The chemical process is straightforward. A cyanide solution drips through the pile to dissolve microscopic gold. This free gold is only recoverable if the liquid can actually reach it. Process engineers rely on gravity to distribute this fluid, assuming the liquid will pull through the pile with uniform coverage. Fluid contact represents the primary bottleneck. No amount of machinery can offset the loss if the extraction liquid fails to touch the gold. Liquids seek the path of least resistance. In a porous heap, this creates channeling, where cyanide rushes down established gaps while bypassing surrounding ore. As channels stabilize, large rock clusters remain untouched. These internal dry zones trap leachable gold deep within. The financial loss is permanent. This bypassed gold remains in the pile, despite being perfectly accessible to the right chemistry. Uniform saturation is the absolute goal, yet gravity alone often fails to push the solution into every crevice. Yield loss is a failure of permeability. The liquid simply refuses to saturate the solid. Operators modify the ore's texture through granulation. Fine powder and clay are bonded to the exterior of coarse rock particles to create a porous coating. This coating prevents clay from migrating, preserving the structural gaps required for the solution to flow. Additional treatments include sizing the ore, washing it to remove soluble salts, and injecting air for more oxygen. These steps optimize the environment, but the fluid still moves according to its own physical constraints. Mechanical preparation has a ceiling. Eventually, maximizing recovery requires changing how the liquid interacts with the rock surface. Surface tension acts as a physical barrier. The leachate naturally clings to itself, causing droplets to bead up or bridge over tiny pores. A wetting agent, a specialized surfactant, is added directly to the leachate to solve this. The surfactant collapses the fluid's surface tension. The droplet loses its spherical shape and flattens against the rock surface instantly. This enables the liquid to wrap around individual particles and seep deep into microscopic jagged crevices that were previously airlocked. Penetration replaces pooling. The wetting agent ensures the chemical solution actually reaches the gold particles hidden in the ore's pores. Total permeability across the heap eliminates channeling in dry zones, ensuring every cubic meter of ore is treated. Leaching cycles shorten. Faster saturation means the gold is dissolved and collected in a fraction of the time. Operating costs fall as the cycle accelerates. Pumping energy expenses and total cyanide consumption drop when the process reaches its recovery target faster. Refining more gold in less time increases the final beneficiation index without interfering with downstream absorption or desorption. Profit depends on the behavior of the liquid. Maximizing recovery is a matter of making the extraction fluid act as wet as possible.